is kind of our what's left tracker over here, right? So this week, the last 4 new material classes are this week. And then we have 2 course review classes next week. So this is actually from a previous semester. So we have 2 on Tuesday and Wednesday. But since we only have 2 classes, usually what I do in these review classes is I ask people to send me problems that they think are tricky, right? So stuff that they think is difficult to solve, right? Maybe something that you haven't seen before, some kind of weird variation on a problem. And then I'll do those in class. So we'll talk about maybe what problems we might do, but since we only have 2 review classes, if people are interested and they want to send me some other problems, I would be okay sort of taking those problems and then making a video of me just doing the solution. And then it's kind of another resource for you if you want to do that. Because as you see, especially with the homework type problems, it often takes a whole class to get through one of these cycle analysis problems when the state table is as blank as we see in the homework problems. So, and again, it'll be, my thought is 10 multiple choice questions and 3 long answer problems on the final. If people are really passionate about the idea of having more multiple choice, 20 multiple choice and 2 long answer problems, you can let me know. But I find that people tend to prefer fewer multiple choice questions where there's no partial credit and more long answer problems where there is partial credit. So that was going to be what I was going to do. I think for those long answer problems, the thing that we've done since the last exam is cycles, right? And we're going through them really fast because we got 4 lectures a week, right? So I think you can certainly expect those long answer problems to be different cycles, right? And there's different things, right? So think about the questions that we know, right? How do we characterize the cycle, right? How do we, what's the next question? Is it open or closed when we look at the different processes, right? And then is it, what's the fluid, right? So there's different permutations of these things for these different cycles, and you can expect to see that. And then the multiple choice that we get on the final is maybe a little bit different than what we've seen in the previous case, because I think we do maybe 5 cycles, and there's only 3 long answer problems. So then typically what I do in the multiple choice part of the exam is, maybe there's a figure with the state table and like a picture of a cycle. And then maybe there's 2 or 3 questions that are associated with that picture, right? And the way that I do it, because we have to do it online, I would put that picture in each one of the questions. And then they won't like chain together, right? So it's like, I'll ask the questions in such a way that, if it's questions 6, 7, and 8, then you don't need the answer from number 6 to do number 7, right? So it won't be that because you got the one wrong, you get the other one wrong too. So, again, the state tables there will be probably more filled out than you'd see in a long answer problem. And maybe it says something like, what's the net work, right? Or net power. And it's got all the information about the turbines and pumps. And then you calculate it, right? Or maybe it's got some state information for what's going into a regenerator in a Rankine cycle, and it says calculate Y. And then you sort of use the information that's there to calculate it. Right, so that's kind of the idea. Again, if you have questions about the exam, I'm happy to answer them now, or you can shoot me an email, or we could talk about it in office hours this week too. So does anybody have any questions about how we'll proceed with the exam? So my plan is, I think it's the Monday, the 9th, right? I think I've talked about this before. And I was going to have us start at the same time that we had started before. But we'll go we have 1 extra problem, right? So that's 35 minutes plus the 5-minute, no, it's 40 minutes plus the 5-minute grace period. So it would go 45 minutes later. So I think we'd be done sometime after 9 o'clock. So, but I know people work, because I was also thinking about maybe starting at 6 instead of 6:30, but I know that could get tricky with people's work schedules. So my plan is to start at 6:30, and then if you have alternate timing for your exam, we can talk about when you'd prefer to start that exam too. Okay, if there are no further questions, then I will get on with what we're talking about today. So the first thing that I like to do, kind of, especially after we get these weekends, right, is kind of review a little bit what we've been doing, right? So we talked about these Brayton cycles, right? In Brayton cycle, it's almost the same as a Rankine cycle when we think about our three questions, right? So it's a heat engine, so we need to know the net power and the heat in, right? That's how we characterize the thermal efficiency. It's a series of open system processes. So we'll be using the open version of the first law and getting things like W dot is equal to M dot times H in minus H out. But then it differs from the Rankine cycle because its working fluid is ideal gas or air, right? But because it's a heat engine, the way we characterize it is going to be with thermal efficiencies. And then we might also want to know the back work ratio. Right, so that's, recognizing that the power plant is the first consumer of the power from the power plant. So we want to say how much of the power developed by the turbine, or the turbines if it's more complicated, goes into the compressor. It's important, I think, to know how to draw these PV and TS diagrams. I think for me, for the open system ones, I think the TS diagrams are more important. But for the closed system ones, which are our internal combustion engine cycles, I think it's more important to know the PV diagrams. But this is kind of one of those things, especially since it's an open book exam in the summer, because it's online, to just have these PV and TS diagrams available to you while you're writing the test, so that you, if you're asked to write them, then you can draw them, right? But also, you can identify on a TS diagram, you can identify where the isentropic processes are. And when the working fluid is an ideal gas, the trick to solving the states, one of the tricks to solving the states anyway, is knowing where those isentropic processes are. Because with ideal gases, when we have an isentropic process, then we can use that those isentropic relationships, right? And remember that they're different if we're cold air standard, if we're constant specific heat, or if we're variable specific heat. So because it's a series of open systems, we're going to make the assumptions that we usually make about open systems, right? That all components are steady state. We're going to neglect kinetic and potential energy, and they're one inlet and one outlet for this case. And then we're going to say that when we're talking about the combustors and the turbines and the compressors, that they're either adiabatic or passive. And when we do that, we'll get that if we're trying to solve power, we get M dot times H in minus H out. And if we're trying to solve for a heat transfer rate, we'll get M dot times H out minus H in. And then once we have these expressions, we can sum these back into our, say, how do we find the thermal efficiency, right? So we find the net power and we find all the heat in. But here's the trickiest part, right? So we need to find where the processes are isentropic. Because where they're isentropic, then we're going to say, we're going to have to use these isentropic relationships that we have. And the isentropic relationships are different if it's variable specific heat or an air standard analysis, or constant specific heat or a cold air standard analysis. So if it's variable specific heat, in our equations, when we have delta H, we're actually going to find the individual values of H, right? So to do that, we're going to look for an isentropic relationship, right? So our options are either P over P is equal to PR over PR, or V over V is equal to VR over VR, right? Those equations are on your equation sheet. Now, typically, for open systems, we're going to know pressure ratios. This is hard for me to say, but for these Brayton cycles, we often talk about a compressor pressure ratio, right? So we'll often know the ratio of pressures, right? And then because we can usually fix one of the states at a turbine or a compressor, we'll know one of these PR values, and then we can use this expression to find the other PR value. The nice thing about that is when we use table A22, all we need to know is one piece of information, right? We're used to needing to know how to use the temperature, and then we go from left to right across that table to pick up, say, H and PR. But when we're at the exit of these turbines and pumps, or turbines and compressors, typically we'll know PR from this equation, and then we'll move from right to left across the table 822 and find the H value and then find the temperature if we need it. Now with cold air standard, it's kind of the same, right? But it's a little bit different, right? It's just a little path, a different path in this choose your own adventure. So we still need to know where the isentropic processes are, right? So the difference with cold air standards, right, or constant specific heat, is that we never have to find the individual values of the enthalpy. Everywhere we have delta H, we're going to substitute Cp times delta T, right? And typically, for a compressor or a pump, we'll know the inlet but not the outlet, right? So now, again, we've got two expressions to choose from. They both have K in the exponent. So this is how we know it's constant specific heat, because remember, K is Cp divided by Cv, and we have K in the exponent here. So this is a constant specific heat expression. It also says on the equation sheet, equations for isentropic ideal gas. It might say with constant specific heat, but I don't remember. But again, we're going to have two options, right? One of them has K minus 1 over K in the exponent and a pressure ratio. The other one has K minus 1 in the exponent, but a volume ratio. So again, for open systems here, we're going to probably know the pressure ratio and not the volume ratio, or not the ratio of specific volumes, right? So here we're probably, for open systems, going to use this expression. Whereas for ideal gases, it's the same thing. We look for, where for internal combustion engines, we were still looking for these isentropic processes, but we usually knew the volume ratio. So we used a different expression. And because it's an ideal gas, you can also always use the ideal gas law. It doesn't have to be isentropic. You can always use the ideal gas law between states. So after we talked about the basic Rankine cycle, we talked about how to improve efficiency, right? And the first way we talked about was doing a regenerator. Regenerators are easier, I think, to solve for Brayton cycles than for Rankine cycles, because here we don't split the mass. Instead, when we come out of the compressor, we go into this regenerator, right, before we get to the combustor. And the reason that we do that is we're taking this exhaust gas from the turbine, and it also goes through the regenerator. So we have hot exhaust gas through this upper leg of the regenerator and cold compressed gas through the lower leg of the regenerator. And what happens here is, even though the mass doesn't mix, heat is transferred from the hot leg to the cold leg, right? And because of that, we're reducing our outlet temperature, but we're increasing the temperature where we go into the combustor. So we can get to whatever temperature we want by burning less fuel, right? So that's how regeneration increases efficiency, right? We talked about, for regeneration, if we're talking about this heat transfer rate in, it'd be m dot times h out minus h in, if we can make all the assumptions we usually make, right? And without regeneration, we go from state 2 to state 3. But with regeneration, we only have to go from state X to state 3. That the regeneration gives us this. It's not really free. It's just we've already paid for that heat, right? So instead of dumping it out into the atmosphere, we're reclaiming some of that heat. The other thing we talk about with regenerators is this regenerator efficiency. So here we talk about the actual amount of heat, right? That's Hx minus, so the H out minus H in of the regenerator, divided by the maximum amount of heat we could transfer, right? Now, since state 4 is the highest temperature of the exhaust gas when it goes in, state X, the highest temperature state X could have, the highest enthalpy state X could have, is equal to the enthalpy at 4. Right? So this regenerator efficiency is going to be Hx minus H2 divided by H4 minus H2. Don't get too caught up with what these numbers are, because if the cycle is a little bit more complicated, if it also has, say, reheat or intercooling, then the state numbers might be different, right? So remember that this is the actual amount of heat transferred into the fluid in the regenerator divided by the maximum amount of heat that gets transferred into the regenerator. So don't memorize the state numbers, understand the concept. As I said, we can do reheat just like we did with Rankine. So here we split our turbine into two turbines, a high pressure turbine, right? We come out of the combustor into the high pressure turbine. But then we come out of the high pressure turbine, add some heat, and then go into the low pressure turbine, right? And doing that adds this extra bit of area on our TS diagram, which means we're increasing the net heat, but we're also increasing the net work. The cool thing is when we use reheat and regeneration together, then we get some beneficial coupling, right? Or maybe synergy, I think is the sort of business word for this. Basically, because our exhaust temperature from our second turbine is higher than it would be if we just had one turbine, then now we can get more regeneration because basically there's more heat in this state 4 than there was before. Doing reheat, it increases the work we have by producing more power, right? So that's how it increases net work. But in Brayton cycles, because the back work ratios are reasonably high, especially compared to something like a Rankine cycle, we can also improve our net power by reducing the amount of power we put into the system, right? To do this, we add cooling. So again, now we're going to split the compressor into 2 parts. And instead of heating in between, we're going to cool in between. And that adds this little bleb of area down here, which also increases our net power. But here the net power is increasing because it takes us less power to compress the fluid. So that's Brayton cycles, right? And now today we're going to talk about turbojets. The good thing about turbojets is that they're Brayton cycles. So the center of a turbojet is a sort of basic Brayton cycle. The bad thing about turbojets is here at the front, we have a diffuser, and here at the back, we have a nozzle. That means that in the turbojet, kinetic energy is really important, right? And anytime kinetic energy is important, right, the hairs on the back of our neck stand up because the units become kind of a bear, right? It's bad in metric, and it's worse in imperial, right? So, when I start this, if I ask my kids, so when I, started teaching this, I was kind of talking to my kids about it, right? And I was like, well, what do we need to fly, right? And, their answer, inevitably, right, because they were younger than they are now, is, faith, trust, and pixie dust, right? And it never hurts, right? But this is not how airplanes fly, right? It's a shock to you, I know, right? But, in the airport, we're not just sprinkling a little dust on top of it and then it flies away, right? Instead, right, you've maybe seen a picture like this. So a plane has wings, right? Again, shocking, I know, right? But, a lot of engineering goes into what does the shape of the wing look like, right? Because what happens here is as air flows over the wing is designed in such a way to create high pressure under the wing and low pressure above the wing. The reason that we like that is that then there's a net upward force, right? Because the pressure under the wing is pushing it up, right? So then there's this net upward force, right? And we call that force lift. But lift only happens when there's air flowing over the wing, right? And it's not like you just sit around at the airport waiting for a really windy day, even though it's Rochester, right? So it's almost always really windy, right? But in order to get lift, what we need from the plane, from the engine of the plane, is thrust, right? So what the engines on the plane do, right? What these turbojet engines do is they push the plane forward really, really fast. So then even if the air is still, right? Then if you were like a crazy person standing on the wing, right? It would feel like the wind is blowing in your face, right? So that's the job of the turbojet, right? It's developing thrust to push the plane forward, right? So it turns out it's not faith, trust in pixie dust. It's thrust that we need here, right? This is my favorite dad joke of the whole class, right? So this is, it's all downhill from here. It was probably all downhill before this too, right? Right. So what is thrust, right? You're not going to have to know this on an exam, but because all of the cycles that we talk about, I'm really big on talking about it's the energy benefit divided by the energy cost. So even though a turbojet is a heat engine, it's really, really important for us to remember that it's not trying to maximize mechanical power. So it's different than all of the other heat engines that we talk about, right? It's trying to develop thrust, right? So thrust is a force. And the equation for thrust is change in momentum over time, right? Momentum, remember, is mass times velocity, right? So this is mass times the velocity of the air at the outlet minus mass times the velocity of the air at the inlet divided by delta T, right? So really, the job of the turbojet is to increase the airflow, the speed of the air that comes out the end. Really the, not just the speed, I guess, but the momentum going out the back, right? Right, so we could write this as the mass divided by delta T times the velocity, right? Both of these terms, right? And if we took the limit as delta T went to 0, this would be like the mass flow rate at the outlet times the velocity at the outlet minus the mass flow rate at the inlet times the velocity at the inlet. Right, so this is good, but this is a force, right? But this is thrust, right? This is how much thrust is developed by the engine, right? And because there's only one inlet and one outlet in the turbojet, there's only, in all of the components in the turbojet, right? There's only going to be one mass flow rate. So mass flow rate at the outlet is going to be equal to mass flow rate at the inlet, provided we're at steady state, right? That's what conservation of mass is going to tell us. So we could write our thrust force as m dot times V at the outlet minus V at the inlet. But what if we wanted to write a thermal efficiency for these turbojet engines? Now, I'm not going to ask you this on the exam. I don't even think they talk about it in the textbook, but we've talked about this way of characterizing all of these engines in the past, right? So this is the desired energy effect divided by the energy cost, right? And it's a heat engine, so the energy cost is going to be the same, but it's different than all the other heat engines, right? So on the top, we still want a power, but it's not mechanical power, right? It's not going to be the power of this spinning shaft. Instead, it's going to be the power of the thrust. So how do we go from thrust force to thrust power? So thrust power must be in kilowatts, right? So power is like energy per unit time, right? Kilowatts is kilojoules per second. And kilojoules is kilonewton meters, right? So right now, we have a way of finding the thrust force in kilonewtons, at least if we were talking about metric, right? But if I look at this, it's like kilonewtons multiplied by meters divided by seconds, right? Or multiplied by meters per second. So this is like times the velocity. So if I took the thrust force that I have and I multiplied it by the velocity of the engine, then I would have a thrust force. So we can think of this thrust force as the thrust, or the thrust power as the thrust force times the velocity of the jet. All right, so I could write it like this if I ever wanted to do this, which I'm not going to ask you to do on the exam. Right? But our thrust power is going to be mass flow rate times the change in the velocity across the engine multiplied by the velocity of the jet. Right? The velocity of the airplane. So if you were like standing on the wing, how fast would you be moving relative to the ground? Right? So if I wanted to, energy cost, because this is the heat engine, right? This is still the same thing, right? So we're burning jet fuel to make heat, right? So our energy cost is this heat rate in, right? So that's the same. The denominator here is the same as all the other heat engines that we've talked about. So if I wanted to write an equation for this, right, I could write the thermal efficiency as m dot times delta V over velocity of the jet divided by the heat rate in. Right, so I can think about a thermal efficiency of this particular type of engine, even though I don't think they do this in the textbook. And I know, just to keep this summer class, even though I'm the only person teaching it, in line with what we would teach in the fall and the spring, where other instructors maybe don't even talk about this, right? So this won't be on the exam, right? So part of the tricky part here is that we want the velocities relative to the moving frame of the jet, right? But again, you don't have to worry about this thing, right? So here's how we start to solve this Brayton cycle, right? Or turbojet engine, right? Because it's really a Brayton cycle in the middle, right? Here's a compressor, here's a combustor, here's a turbine. But the difference is we've got this diffuser on the front and we got this nozzle on the back, right? We're always in this class going to pretend that the air is still. There's no like headwind or tailwind. I don't know if anybody's ever flown a plane. My wife took flying lessons for a couple of years, but she's colorblind, so she could never do it by herself past sunset, right? Because the lights on the plane are red and green. It's so silly that it's like the two most important colors we have are red and green for like driving and things. And I also think the most common form of colorblindness is red-green colorblindness. So like, stop and go. Those are two different, but it's kind of like if you've driven a boat too, you pass on the green side of the two lights and you don't pass on the red side, right? Right. So here, right, we got a jet, right? And our turbojet engine is basically a Brayton cycle, right? But it's got the diffuser and the nozzle at the end. Now, we're going to pretend that the air is still, right? But that we're kind of a crazy person standing on the wing, right? So it's going to look to us on the wing, not like the plane is moving through still air. It's going to look to us from our frame of reference that the plane is still and the air is blowing in our face, right? So we're going to talk about this moving frame of reference, and the velocity of the jet is going to be the inlet velocity, right? And this is why we put the diffuser at the beginning, because there's going to be a lot of kinetic energy then associated with the air that's going into the diffuser, right? And the purpose of the diffuser's job is to take this energy in terms of kinetic energy and turn it into enthalpy, right? So that's as we go from state A here to state 1. They kept the numbering the same as a Brayton cycle, right? So it goes 1, 2, 3, 4. 1 is into the compressor, 4 is out of the turbine. So then they call this inlet state A. I guess that's supposed to be less confusing, right? So that the numbers stay the same, right? So the turbine or the diffuser looks kind of like a compressor, right? What it's doing is it's increasing the temperature or the enthalpy of the fluid, right? But it does it not by adding mechanical power, but by scavenging that kinetic energy of the fluid that's coming into the diffuser. Now, the purpose of the whole jet, right, is to get as much velocity as we can coming out of state 5. So as we move from state 4 to state 5 in the nozzle, just like we go through the turbine, right? What the turbine's job is to take the enthalpy that's in the fluid and turn it into mechanical power, right? So that's happening here as we drop from 3 to 4. The nozzle acts like a turbine in that it's taking enthalpy out of the fluid, but it's not turning it into mechanical power because that's not the point of a turbojet. The point of the turbojet is to maximize the thrust, and the way we do that is by getting the air to move as fast as we can out the back of the jet. So as we take down the enthalpy here from 4 to 5, what the nozzle does is it takes that energy and turns it into kinetic energy at the nozzle exit, right? And this is the thing that's, one of the things that's the most difficult about the Brayton cycle is that these kinetic energy terms in the diffuser and the nozzle are important. I remind myself that they're important at the states that don't touch the rest of the jet, right? So the inlet, which is not connected to the Brayton cycle in the middle, kinetic energy is important because we take the kinetic energy in and we're going to turn it into enthalpy. And kinetic energy is important at the end of the nozzle, which also doesn't touch the Brayton cycle that's in the middle, right? So you can neglect kinetic energy everywhere except the very inlet and the very outlet of the jet, right? So what we're trying to do is maximize the outlet velocity. Now, in between, we have this Brayton cycle. So this is, I guess, a 3-component Brayton cycle, right? But it's the normal Brayton cycle that we talk about almost, Now, the thing here if we talk about common things that people make mistakes on the exam, right? One of the big things that people make a mistake on for this Brayton cycle is what to do here at state 4. Because if this was a Brayton cycle, a normal Brayton cycle, we would say that the pressure at state 4 is the pressure at state 1. And in a normal Brayton cycle, we can do that because state 1 and state 4 both touch the atmosphere, right? The outside air. But that's not the case here, right? These are both now internal to the system, right? And the pressures here are not the same. So the thing we have to remember about the turbojet is that it's trying to maximize the thrust, right? It's trying to run this turbine to generate as little power as possible. Now, the power that we definitely need to do for this Brayton cycle that's in the middle of our turbojet, the turbine needs to generate enough power to run the compressor. And that's it. So the Brayton cycle in the middle of the turbojet engine has a backwork ratio of 1. Write this down because it's important and it's something that people often forget when they're doing these problems. And this always happens, or at least often happens, right? Is you get halfway through a problem and you're going through, you're fixing your states, you're feeling good about yourself, and then you get to this one part and you're like, oh, I don't know what to do. And then it can feel like there's nothing left to do. You just feel stuck, right? So again, that's why I encourage symbolic solutions all the way through, because then your pages won't be blank, right? And you'll demonstrate your understanding. But the way to get stalled in this particular problem is to forget that the backwork ratio is 1, right? So the turbine power is equal to the magnitude of the compressor power, right? But the signs are opposite. So this, in a nutshell, is a turbojet engine. But we'll go through all the different components, right? This is how you draw the TS diagram. If you look at the diffuser, you draw this just like a normal Brayton cycle, right? It's just you put A as the inlet and state 1 is somewhere up this vertical line. And then you put state 5 as the outlet and state 4 is somewhere in between state 3 and state 5. So how do we solve this problem, right? So if we're trying to go through and we know now all the different states, right? Or at least if we had to find like a thermal efficiency, we could do that. We got an equation, right? So now we want to have all the states so that we can write down numbers, right? For our symbolic solutions. So the purpose of the diffuser, right? If we go step by step. So my encouragement to you when you're doing these is march on through, right? So start at state A and go all the way to state 5. The purpose of the diffuser is to maximize the enthalpy at state 1. So it's trying to take the kinetic energy of this air that's coming into the diffuser and turn it into enthalpy. So if we were doing a first law on this diffuser, we're going to say that it's at steady state, that it's 1 inlet and 1 outlet, so the summation signs go away. We're going to neglect potential energy, but we can't neglect kinetic energy change because that's the whole purpose of the diffuser, right? But here we can say that it's both adiabatic and passive. There's no fan blades in here, and we're going to assume that it's well insulated. Here's what we can do. We can't say that the kinetic energy change is negligible, but we will say that the kinetic energy at the outlet of the diffuser, the kinetic energy at any of the states that's touching the Brayton cycle in the middle, right? So that's the exit of the diffuser. We're going to say that even though that velocity is not 0, we're going to say its kinetic energy term is not that important. That we're essentially scavenging all of the kinetic energy and turning it into enthalpy. So if I do that, then my equation, if the problem is metric, is going to look like this. H1, so that's the enthalpy at the exit of the diffuser, is equal to the enthalpy at the inlet of the diffuser plus the kinetic energy that was there, right? So what this equation is saying is we took all that enthalpy at the inlet and all that kinetic energy at the inlet, and we turned all that kinetic energy into enthalpy. So we raised the enthalpy by that amount. Now, if you look at this equation, hopefully your spidey sense is tingling, right? Because this kinetic energy term sticks around, that means that we got a problem with units, even in the metric system, which is usually friendlier, right? So we need to think about what's going on with the units, right? So typically here you would divide by 1,000 if this was in meters per second, right? So this units would be tough, right? So this is what we do with the diffuser if we have a metric version of the problem. But if we have an imperial version of the problem, the equation's not quite the same, right? Because in the imperial version of the problem, the kinetic energy term in the bracket, we had to divide by GC just to get to energy per unit mass, right? And even after we do this, the units still aren't going to be right because our velocity maybe is going to be in feet per second. And if it's in feet per second, then we want it in, this, we're going to get foot-pounds per pound mass here, and we want to get BTU per pound mass. So probably here, I'm going to have to divide this term or multiply this term by 1 BTU divided by 778 foot-pounds, right? Just like in this term, I probably am going to have to multiply by 1 kilojoule per 1,000 joules, right? But just to get to the right quantities as energy per unit mass, I got to divide by that GC when I'm dealing with imperial units, right? So the diffuser and the nozzle, we always got to be aware of the units, right? Because the kinetic energy term makes life difficult, right? Otherwise, you're just going to get a massive number, right? So if you get an enormous number, it's probably a unit issue, right? So that's the diffuser. Now, here in the normal part of the Brayton cycle, right? This, we're going to solve this just the way we normally do, right? So here, what we're trying to do is maximize H4. So there is one difference, and that one difference is that the back work ratio of the Brayton cycle in a turbojet engine is equal to 1. So we're only using the turbine just to run the compressor because we want as much enthalpy here at state 4 as we can, because we're going to take this enthalpy down as much as we can to get as much velocity as we can out the nozzle, right? So in this Brayton cycle, we're going to say all 3 of these components are at steady state. They're all 1 inlet and 1 outlet. Here, because we're in the Brayton cycle, we're touching the Brayton cycle because we're in the Brayton cycle. So the kinetic energy in the engine can be neglected, and the potential energy changes in the engine can be neglected. And then we're either going to say these components are adiabatic, if it's the compressor or the turbine, or that they're passive. We'll neglect any kind of friction losses that are connecting the different components, and we'll neglect heat losses between the lines, right? So when we do that, we get these equations that hopefully by now we kind of know and love, right? That if we're talking about the turbine, it's going to be m dot times h in minus h out. If we're talking about the compressor, it's also going to be m dot times h in minus h out, but the sign will be negative here. And then that combustor is going to be m dot times h out minus h in. And there we're adding heat, so it's positive. Now the big thing, the thing that people forget, the thing that trips people up, right, is that they want to, at state 4, make the pressure at state 4 the same as the pressure at state 1. That is not the case. What you need to do for this Brayton cycle is make the back work ratio equal to 1. We're only running the turbine so that we can run the compressor, right? And this is the thing that people get wrong about this cycle. I guess uniquely wrong about this cycle, right? Because it's not in the other ones, right? So because this back work ratio is equal to 1, right, then the compressor power, which is equal to m dot times h1 minus h2, is equal to the negative of the turbine power, which is m dot times h3 minus h4. I can cross out the mass flow rates, and I can get this expression. Probably, we're going to want to solve for h4 from this equation. So I'm going to say it again. The back work ratio of the Brayton cycle at the center of a turbojet engine has a back work ratio of 1. Right? That's important. Right? So now we're through the turbojet, or we're through the Brayton cycle part of the turbojet, and we have the nozzle left. Right? So let's do the first law on the nozzle. Right? We're trying to maximize V out, so I cannot cancel the kinetic energy term at the exit, right? Because that's the job of the nozzle, is to take enthalpy and turn it into kinetic energy. So this is kind of like the diffuser, but it's different because we're interested in the exit kinetic energy. So this nozzle is at steady state. It's one inlet and one outlet. We're going to neglect changes in potential energy. We're going to say that it's adiabatic and that it's passive. And we're going to neglect the kinetic energy of the state that touches the Brayton cycle, which is the inlet of the nozzle. Right? So if I do all of this, right, I'm going to see that the enthalpy at the inlet is going to be equal to the enthalpy at the outlet plus the kinetic energy at the outlet, right? And that's what this equation tells me, right? Except I've rearranged it to solve for the velocity at the exit, because probably that's what you're going to need to find. Again, this is in metric, but the kinetic energy term is still an issue in metric, right? Probably here, if our velocity is in meters per second, we're going to have to divide by 1,000 here, right? But again, what happens if we have imperial units, right? Then life becomes a little bit more difficult, right? Because we took that velocity term and we got to divide by GC, right? Because otherwise it's not energy per unit mass, right? But then we're still going to have this thing where we got to multiply by 1 BTU divided by 778 foot-pounds, assuming that my velocity is in feet per second. I like the caption on this one if you didn't get a chance to read it. Right, so the nozzle is kind of like the diffuser, but the diffuser, we're interested in the kinetic energy at the inlet, and the nozzle, we're interested in the kinetic energy at the outlet, right? And the units with the kinetic energy term are always going to be an issue. Doesn't matter if it's metric or imperial, they're difficult, right? So if I can make all the assumptions that I'm usually going to make, these are the expressions that I expect to have, right? Compressor and turbine powers are m dot times h in minus h out, but they have the same magnitude, right? Just the opposite sign. My combustor is m dot times h out minus h in, right? That's just normal. The diffuser, I'm taking the inlet enthalpy, or I'm taking the inlet enthalpy plus the kinetic energy and turning it into the outlet enthalpy, right? So I'm trying to scavenge that kinetic energy that's at the inlet and turn it into enthalpy, right? Because that means I do less work at the compressor. And then what the nozzle is doing is the opposite, that it's saying the difference. So ideally, we could drive this enthalpy at the exit down to 0, but that's not how life works, right? Because there is some pressure at the outlet and we can't drive that temperature down to absolute 0. So we're just going to try to minimize H5, right? And then we want H4 to be as high as it can, because the difference between H4 and H5 is what's going to generate that kinetic energy for us at the exit of the jet. So this is kind of a typical turbojet engine if we're in the metric system, right? If we're in imperial, and we still got to worry about the units, because these say velocity squared over 2, but I only do that because I don't know what the velocity term is going to be, right? I could put this over 2,000, but that would only be true if the velocity was in meters per second. If I gave you a velocity in kilometers per hour, right, which is probably how you'd actually measure the speed, right, or at least potentially, right, because the numbers are pretty big, then you'd have a totally different conversion, right? So here I'm just putting it as at the base level, and then you have to worry about the unit conversion. Again, life is always harder when you're using imperial units, right? Write to your congressperson, right? Maybe we can get this thing changed. Go to the metric system here in the US, right? It's different because the kinetic energy term, we got to divide by GC, right? Because otherwise we don't have energy per unit mass, right? So we can't add those things together if they don't have the same type of unit. But even after we do that, we're probably not going to have the same units, even though they're the same like quantity, right? So from this, we'll have the right quantity, but we'll probably have to multiply the kinetic energy terms by 1 over 778. which is, I guess, like the imperial version of 1/1000, right? Because you can't have nice round numbers. It's just you can't. So this is how we do it in imperial, right? And again, we always got to worry about the units in the nozzle and the diffuser, because the kinetic energy, anytime kinetic energy sticks around, right, your spidey sense starts tingling. You say the units are going to be a pain. Characterization, again, I won't talk about this too much because it won't be on the exam. But if we did all of this stuff, right, then now we've got equations that we can put in here and find the answers, right? To do this, we would need this exit velocity. So you would have had to do that whole, you know, the whole cycle analysis to find out what the exit velocity was. So the complexity you could add to a turbojet engine is adding an afterburner. Now, this is not going to be on a passenger airplane, right? But could be on a military airplane, right? Because when you do this, you burn a lot more fuel, right? And fuel is expensive. So when we're just, you know, flying back and forth to, I don't know, London or wherever you're flying to, you know, it's not worth the extra cost and the extra emissions, right? But when you're talking about a military application, then, you know, cost is still important, but it's maybe not the primary driver, right? So what we do is we have a normal turbojet engine and then an afterburner at the end. An afterburner, the way I think about it, it's kind of like reheat, right? So what we do with the afterburner is we burn some more fuel, right? So we add some more fuel into the air fuel mixture and we burn it. So what that does is it increases the enthalpy before we get to the nozzle. So all this happens before the nozzle, right? And now, because we have more enthalpy going into the nozzle, we'll get more velocity going out the back, right? So this is a way to get more speed, right? How do you get faster, right? But it comes at the cost of burning more fuel, right? So this increases the enthalpy at the nozzle entrance, which means that we're going to increase the kinetic energy that we get out of the jet, which will also increase our thrust power. So this is what a TS diagram for a afterburner problem would look like, right? And this is assuming that all of the turbines and the compressors are isentropic, and also the nozzle and the diffuser. There's equations for how to deal with isentropic efficiencies for diffusers and nozzles. Diffusers are basically the same thing as compressors, where you know, the thing that we're getting is the cost, right? And the nozzle is more like the turbine, where the thing that we're getting is the benefit, right? So whether or not it's ideal over real, you can figure out from there. But the equations are on the equation sheet if you ever have to figure them out, right? So here, right, we same as the beginning, we go through the diffuser, nothing changes. The compressor, nothing changes. The combustor, nothing changes. Here through the turbine, we remember that the turbine power is equal to the compressor power in magnitude and opposite in sign. But now, after 4, we would add some more heat, right? And typically, a problem would tell us either how much heat we added or what the temperature at state 5 was. And then once I knew the temperature at state 5, then I could go isentropically down to state 6. And this would have a higher velocity than if we went straight from 4 down to whatever the other state would. I guess it'd be, I don't know, 5 prime or something. Basically what the velocity would be if we weren't using the afterburner. All right, so again, this is not for, you know, they're not doing this on American Airlines, right? But they would do this on military aircraft. Oh, it looks like I got something in the chat. Hopefully this hasn't been waiting here forever. Oh yeah, so we do have somebody who had a chance to fly a small plane. That was my wife. My wife was flying a Cessna. So she did lessons for 2 years. It sounds like it was pretty cool. I don't know. I guess it's probably like when you're learning to drive and there's the person beside you that's got the like pedal on the floor and stuff. I'd be worried about killing myself, but maybe I'm too risk averse sometimes. So that is turbojets. Next class we'll do a turbojet example, and then the following 2 classes we'll talk about vapor compression and refrigeration, which is essentially Rankine cycles running backwards in order to try to control temperature instead of generate power. But that was all that I have for you all. Stick on the line in case people have questions. But otherwise, have a great day.
Have a good rest of your day.
Thanks, you too.
Thank you.
Thank you, Professor. See you tomorrow.
Sounds good. Thanks.